Hello, everyone. This is Professor Jeff Wilkerson at Luther College with an introduction to exercise 24, color magnitude diagrams of open star clusters from astronomers as observers and experimenters as published by Kendall Hunt. So we're going to look at this. This is a great exercise. This is one of my favorite exercises in the entire lab book. And we're going to look at it a little bit, give you an introduction today. Of some things to look out for and some things to think about as you do this. As we talk about at the beginning of this exercise in the written manual, the open star clusters are fabulous, fabulous laboratories for studying stellar evolution. And this occurs for a couple of reasons. One of them is they're all born out of the same cloud of gas at the same time. So all the stars are the same age. Within a given cluster, every single star is the same age, more or less. I mean, within a really close approximation there. So we don't have to worry about age differences. If the stars look different within the cluster, then it's not age difference that's causing that difference within the cluster. If this cluster A, looks different from cluster B, then it might be the age difference between cluster A and cluster B that matters, that causes that difference in appearance. So these are things that are interesting for us. Plus, if they're all born out of that same cloud of gas at the same time, they have very similar chemical compositions. So if star 1 looks different from star 2 within cluster A, star 1 and star 2 is probably not a chemistry difference. It's probably not a difference in abundance of metals or non-metals or whatever it is that astronomers like to talk about. So you can think about this as you look through space and to say, okay, here we are looking out at this cluster. And this is a very vast distance to this cluster. And the actual physical distance is the size of the cluster is very small relative to this distance right here. So that means we can treat all of these stars as the same distance from us to a very good approximation. The stars that are farthest away on this outside edge of the cluster are negligibly farther away from us than the stars that are on the near edge of this cluster. So this is a really powerful tool for us. That means a star that looks brighter is intrinsically brighter. It's not brighter because it's closer to us. It's not noticeably closer to us. So if star 1 looks brighter than star 2, star 1 is brighter than star 2. It's more luminous. So that means we can make a color magnitude diagram where we plot the color down here, say a B minus V color index, or a temperature or something along that, and we can plot the apparent magnitude up here. And this color magnitude diagram, this is what you'll see in the activity here today. So the color magnitude diagrams look like this, right? You see these stars on there. And so when you look at that, the apparent magnitude serves more or less the same function as the absolute magnitude on an HR diagram. So the color magnitude diagram behaves very similarly to an HR diagram in this case for these clusters. So you will see a main sequence emerge. So you'll see a main sequence appear in here. And that main sequence is then these stars. This only works because these stars are all basically the same distance from us. So the apparent magnitude works just as well as the absolute magnitude to see this main sequence where stars are fusing hydrogen into helium in their cores. Now, stars will have turn-off points in this main sequence. So what we're going to do, we're going to walk through in this, we're going to look at several open star clusters, and we're going to look at their color magnitude diagrams, and we're going to try to learn the properties of these stars. We're going to look at 3 things in particular. And I recommend you do all 3 of these things for each cluster in this exercise. So you don't have to keep going back to the HR diagram. You have to go back to the color magnitude diagram of a given cluster and reapplying the overlay. And we'll show you how to use this overlay in just a second. You do it all at once, and then you can get this information. We're going to try to find the age of the cluster. And the age of the cluster is going to come from what we call the turnoff point. And the turnoff point is the point on this color magnitude diagram where the stars are leaving the main sequence. They've fused all the hydrogen into helium in their cores, and they're starting shell hydrogen fusion, and they're leaving, they're curling away. So the turnoff point is up here. At the upper main sequence, you'll see these stars start to leave there, and that's what we're calling the turnoff point. That will give us the age. The next thing we're going to try to get from this is the distance. And the distance will come from getting the, looking at, making a comparison of the apparent magnitude with the absolute magnitude of stars of a given color. You know, a star of this color has an absolute magnitude on the main sequence of a certain absolute magnitude like this. And we can read the apparent magnitude over here. We can say, this star of this color has this absolute magnitude. It has this apparent magnitude. And we can use our old friend that D is equal to 10 to the power of m minus m, apparent magnitude minus absolute magnitude, plus 5 over 5 to get the distance. So we're going to get the distance this way by comparing the absolute magnitude for stars of a given color to the apparent magnitude of what magnitude we see. And then we're going to look at something called the reddening of these star clusters. And this is an interesting thing. There's some discussion questions about this. This is an interesting thing for you to think about. How do we know the intrinsic colors of these stars? We measure these stars, and we sit at the telescope, and we can measure how bright they are through a B filter, what the magnitude is through a B filter, what it is through a V filter, and then we can say, okay, B minus V, that's our color index. And so we know what color these stars are. What color are they intrinsically? By comparing what color they are intrinsically to what color they appear at the telescope, then we get something we call the color excess, or the reddening. So the color excess is going to be how much redder these stars are than what their intrinsic color is. And so this is going to be B minus V observed minus B minus V intrinsic. Okay, so higher number of B minus V is redder. So the reddening, the color excess is going to be this observed B minus V. The stars get redder as the starlight travels through space. They appear redder to us. So we're going to have a B minus V intrinsic. And so we're going to walk through how to do all of this. This is, hopefully by the time you're done with this exercise, you realize just how powerful open star clusters have been in helping us understand things like stellar evolution and properties of stars. And they're just wonderful, wonderful systems to study. And I say that not just because I happen to have been studying one for the last 20 years. I've been taking pictures of the same open star cluster and studying the stars in there for a very long time. Maybe that's why I say it, I don't know. But in any event, these are really, really powerful tools for you to use. So here's what you want to do. That your lab book has an overlay. I've made this on some transparency on a plastic sheet. I've reproduced that overlay right here. So the overlay is the zero age main sequence. And that zero age main sequence, maybe it's hard for you to see on that overlay right there. So I'll show you that it's in on the printed version of the lab book too. It looks like that. That's the overlay. That's what's on the overlay, is that zero age main sequence. And that zero age main sequence is the shape of the main sequence when the stars are zero age. There you go. That's very cleverly named. That you call the zero age main sequence where the stars are at zero age. And so that is going to allow us to say this is what we would expect this main sequence to look like when the stars first start fusing hydrogen to helium into their cores, when they're first actual stars. They fall onto the main sequence. They fall onto the main sequence from this direction, so you will see some stars above here. So this is going to be a tricky part of this exercise. High mass stars evolve so quickly relative to low mass stars that high mass stars will be leaving the main sequence. You'll have a turnoff point up here, and you'll still have low mass stars that haven't dropped onto the main sequence yet for some of these clusters. So they're going to be a little bit of messing around to get this to work for you. So what you want to do is you want to take your overlay. The overlay's in the appendix in the book here, but you can make a transparency like this if you like, if you have access to transparency sheets like this. You want to take your overlay and you want to slide it up and down. You want to align it with the axes of these color magnitude diagrams and slide it up and down. And I'm going to recommend, here's a pro tip for you. when you're working your way through here, don't necessarily work these in the order that they appear in the lab book. Here's a confession for you. I forget why they appear in the order that they do. I think I knew at one time, and I don't know why. But you find one like that one is a great one of the Pleiades, M45. And so it's got most of the main sequence filled in. It's got a lot of stars. It's got a fairly identifiable turn-off point up here. And so you can see this. Some of these have little stubs of main sequences. They don't have enough stars. The turn-off point, it's way down. It's eaten away the main sequence. You can't tell as much. So pick a good one like that where you have a fairly clearly identifiable main sequence. The NGC M11, NGC 6705 is probably a pretty good one too to start with. But Melot 20, that looks like a pretty good one here to start with. A lot of stars and a fairly identifiable curvature of the main off the main sequence. The very first one that you look at there, NGC 457, that's a tough one. It doesn't have as many stars. It's kind of hard to see where that main sequence turns off up here. So I might save that one until I've practiced if I were you doing this work with one of these on one of these other clusters. So you can fill out the table of information on these clusters in any order you want to. So what you want to do is you want to take your overlay and you want to take B minus V 0. This is the intrinsic color. It's plotted on both the top and the bottom of your overlay. For your color magnitude diagrams, the top is B minus V0, but the bottom is B minus V. So on the color magnitude diagrams, you have B minus V0 up here, and B minus V down here, observed color, intrinsic color. And so now you want to align your overlay so that the top axes align. You want your color magnitude diagram of your overlay to line up right there on the top. So as you'll see, what I'm doing right here, hopefully you can see that. I can't actually see how good a job I'm doing lining this up for you. But you see, I want that 1.2 to line up with that 1.2 and that 1.6 to line up with that 1.6 and all the way across there. They don't quite line up at the bottom. Can you see that? Can you see that when 0.4 lines up at the top, 0.4 doesn't line up at the bottom? So measuring what we have on the bottom, say that's 0.4, 0.6, so 0.5 is in there. So that looks like that's somewhere in the neighborhood of 0.45 or something like that, was where the bottom axis, the axis from the color magnitude diagram of the Pleiades, lines up with the zero-age main sequence color there. 0.4 lines up with about maybe 0.45 or 0.44 or something like that. So I take the difference, 0.45 minus 0.4. I just measured the color excess of one of these clusters. Good job. Okay, so we got the color excess measured. Now, in order to measure these other things, what you want to do is you want to slide this. You want to keep this overlay aligned left, right. You want one at the top axis. 1.6 is 1.6, 1.2 is 1.2, 1.8 is 0.8, 0.4, and then slide this vertically up or down, keeping the upper axis aligned until you get a pretty good match with the main sequence right there. You see how that curvature matches and locks on? Now there's noise, so there can be a few stars that are below the axis. You can try to get that to line up more or less centered on that axis. But something like that is a pretty good alignment right there. Notice that there might have more stars above the zero-age main sequence down here, because remember, they're dropping on that direction. As you get up this direction, most of them should be lined up right on. But again, the noise is going to make a big difference. And in this one, there's something called the binary star main sequence along here. You can see it runs parallel to the other main sequence. You can see it right there. So be aware of that. You can see it over here on this one that you see. So you just want to get that main sequence to. Let's go over there and try that one. We go over to this one, get 0.8 to line up with 0.8. This one's got a lot more reddening. I can tell that it doesn't have that much more reddening. I was looking at a bad angle there, but you get those things to line up, slide it up, and something like that's a pretty good match, right? Where I can get this thing to line up pretty well there. Maybe I don't have these things aligned down at the bottom, but you see that match right there? Look at that vertex. You see where that vertex, where these things start to walk off? You've measured your turnoff point, okay? So you've measured your turnoff point right there. And so you're going to see If the zero age main sequence looks like this, as we just saw in what I was showing you, where that Y, that vertex right there is the turnoff point, and you want to measure B minus V0 of the turnoff point. Okay, so you want to measure what color of stars are just leaving the main sequence. So again, you're looking for that sort of Y shape, the sort of vertex of the Y shape, where the data, the pointed dot, the points on the graph are leaving the tracing of the zero age main sequence. Every point, let's be aware of what's going on right here, folks. Every dot on here is one star in this cluster. So every single point that you see on this graph is the data plotted for a single star from the Pleiades cluster. So one dot here is going to be the color of that star and the apparent magnitude of that star. The color of that star and the apparent magnitude of that star. So these are individual stars data that's plotted on here. So this is a single cluster with their star data plotted, and you can see which stars are leaving the main sequence by sliding this thing up and down and measuring the turnoff point. I'm having a hard time holding this and trying to hold this up for the camera, but you can see I've got the top axis aligned up here still, and I've slipped this thing up vertically, and I get pretty good alignment like that. And I can start to see, okay, those stars have clearly left the main sequence, and they merged there. I'm going to call the vertex right around there someplace. Okay, so that's going to be my Y that I've identified. So we get B minus V intrinsic of the turnoff point, and then you're going to be able to go to the back of the lab. Once you know the color of the stars that are leaving the main sequence, you're going to go to the back of this exercise, and you're going to look this up and to say, oh, if B minus V is this, I'm going to come up and I'm going to read this off of here. I'm going to read the age of the cluster from the data that's across here. And this is a semi-log plot. Maybe you've used a semi-log plot before, maybe you haven't. But you take the small number that's here, say 5, times the big number that's below. That's 5 times 10 to the 8th year. So if we get a point that if the B minus V leads us up here, and we come across, we get 4.5, let's say, times 10 to the minus 8th years. 10 to the plus 8th years, excuse me, is the age of that cluster. It would be a pretty young cluster, huh? And so a good straight edge, a good ruler was going to help you do that work in here. So you want to have that available to you as you're working on this lab. Now, the last piece of this is to get the distance. And to get the distance, we need that m minus m. We need that v. In this case, we plotted these as v in here, so it's going to be v minus m. So m, small m apparent magnitude is the same as apparent magnitude v for this exercise. And so what we want to do is if we go back to the data and we do our alignment again. So here we are. We've got the vertical, the horizontal axes aligned at the top. And then we slide this thing vertically and make it match. So right there is some kind of pretty good alignment. We see the vertex of the Y where this thing leaves. And I'm going to look at where the apparent magnitude on the axis that you see through the transparency aligns with the vertical axis, the absolute magnitude on the overlay. So it's close to. You want to do as good a job as you possibly can. You want to get as many digits, and I recommend even measuring the space between these and ticking it off to say the space between 8 and 9 is this many millimeters, and measuring how many millimeters off you are between 2 and 8 to get as much precision as you can, because this is going to go in a power. And when you stick something in a power, if you miss by a little bit, you miss by a lot. In the distance. The distance is going to come out of here in parsecs. This distance is in parsecs. And that distance in parsecs is going to have quite a big uncertainty in it, given a small uncertainty in V minus M. But V minus M you see here is 8 minus 2, or 10 minus 4, or 12 minus 6. Now you want more digits than that, so what I was just saying. But that's roughly speaking. 6 minus 0 is 6, 8 minus 2 is 6, 10 minus 4 is 6, 12 minus 6 is 6. So you see, it doesn't matter which of the numbers we choose on the color magnitude diagram to apparent magnitudes to compare to the absolute magnitudes, as long as we're on this axis someplace and we look at that alignment across there. So you can get m minus m and you can get the distance. So that's what you want to do. You want to go through and you want to fill out your table of information for each of the clusters that's in this book. Remember, you don't have to do them in the order they're printed there, and I recommend that you don't. And so you want to do that, and you've got to get the color excess, the age, and the distance. And then we guide you through ways to think about how to use all of that information and what that information is telling you. So that's an introduction to how you want to go about doing this exercise. Good luck with it, everybody. I hope you have fun. This is a great exercise. It's one of my favorites. Take care. We'll have more for you at another time.